All right, looks like our time has just started up. Good morning, everybody. Hope everybody's doing well. All right, so we've moved into a new area where we're going to be talking on registers and counters, which really isn't completely new. It's kind of a specialized area of what we were talking in the previous chapter, actually. But it's kind of new in the sense that we're going to dig down into a little more of the details of it to get into them. And today's topic we want to talk about is implementing registers in Verilog. So this kind of comes down to a bunch of particular details. And I want you to think whenever you're approaching this, there's kind of a dual relationship here. Whenever you have a design in your head, right, an idea, a concept, it should infer a circuit, components, and things like that. So when you've got an idea, hopefully you'll start imagining a circuit and components along with them. And when you have a circuit and components, you want to be able to go back the other way as well. Okay? And these twofold things, that's our design and analysis loop, but they also relate to our design and our testing. So that's going to be how we're going to think about these. So when we think about how we want to build our registers, we want to think about what we're building it in, right? You can't separate them completely from whatever device you're on. And if we think of Verilog as only a programming language, you'll just get the simulation side to work nicely, which will present a pretty picture of it. What we want to do is when we're implementing that circuit in here, we want to think of what is the machine going to infer from our design that we write at the build phase to make sure it builds the right thing. And this is kind of the communication process underneath. So this is why I get kind of picky and I'm like, oh, I hate this code. Whenever I'm saying those things, it usually means that it's likely to get misinferred what the design you want is, and you might get a different build than what you were expecting to get. And the simulation will look the same because the simulation doesn't actually simulate all the components. It simulates the program you wrote. And then your particular pieces of hardware, when you build them, there'll be some effects of how that goes. And if you don't somehow incorporate all those other aspects, it'll get more complicated. Now we're doing simulation right from your base code. If you look at each of these steps, you might wonder, why don't we, when we go to generate the bit file, why don't we just have one button that says generate bit file? Because that's kind of what we do right now, right? You just generate it, you put it out there, and away you go. So at each of those stages when you're done, there's always those schematics that I've referenced sometimes when people have particularly tough errors and we want to find out what's going on. The schematics are helpful. That's not the only thing you can do, though. It will also generate, and you can do a simulation at each of those build stages. And since it knows the components, it'll simulate at that level. So you can compare your earlier simulation to the simulation at that particular level of, the analysis and the place and route. When it gets to place and route, it knows timing, so it can incorporate timing information. Does that kind of make sense? At each of those stops in a regular, like in an actual engineering build phase, why does it take longer when we can do it so much simpler? Well, they want to make sure no errors are there. So you're going to get a really comprehensive test bench. And then you'll do the first stage of your synthesis. And then you'll run the simulation again, and you'll compare that simulation to what you did before to make sure, are they the same? Is it working? Did any of the things that it picked on its choices, did it make my design no longer do what I wanted it to do? Which often comes down to timing or a little weird parasitics or other things of that sort. All right? If it passes, then we move to the next stage and we check it again. And we want to try to catch it as early as possible because the earlier you catch an error, the cheaper it is. Does that make sense? So what I want us to talk and think about today when we're doing it, right? I mean, we could do this in like a 2-minute job, but of how do you write them. But you won't get the idea of how to infer the design. And so the infer the design and to do the test code, this is kind of my overview of what my concerns are for the day. Right? We want to make sure we get the right design on our platform and that we can verify it early. All right, that's kind of my goals. All right, let's consider our simple ones. Let's do the easiest of all of our things, a single D flip-flop. And typically we talk about D and Q and a clock. That's the most basic thing. So if I only have D, Q, and a clock, how can I write this if I just want this? Well, I have to start by building a module, right? And maybe I'll call this one a D flip-flop, DFF. And then I need to handle my inputs and outputs. Okay? At the moment, I said I only have these. So I'm going to pretend I have no reset. Does that make sense? When we'll add resets, we'll add other signals as we go. But I want you to think of how they relate and where do I put them. Okay, so I only have these three right now. Hey, and this is as simple as it gets because you can't do a flip-flop with less than this. I have to have clocking because otherwise it's not a flip-flop. I have to have the data that comes in and the result that you're stored. Okay, so I've got my input. I can look at this. My input, it's a single bit, which clock is my most important, and then D, because without a clock, it's not a flip-flop. And I've got my output, which I'm going to make a reg for Q. And whenever I say reg, what does that tell you? All right, reg means I want to change it inside and always when I'm dealing with synthesis. If you're dealing with simulation, it'll be inside an initial or an always. But you really shouldn't use initials for synthesis. Okay. So whenever we're building something that involves state, we said we're going to split them into kind of components. In this case, we're just building the memory. So we're going to have our first part, which will be our always. Now, I've mentioned in labs there is this option, so maybe I'll color code this. I can do an underscore FF, or not. So that's why I put it blue here. Okay. The underscore FF is a system Verilog extension to basic Verilog. So these underscore and then a name, and the varieties are underscore FF, and there's underscore latch, and there is underscore comb. So these are kind of my always varieties. Always, and add one of these. If it's flip-flop, it will automatically know. You've just told it in advance, build me a flip-flop. So remember we were saying we wanted to be able to capture the design intent for what's going in? This is really helpful because I'm not asking it to infer it. I just tell it. Okay? Which means inside this, I really would like to ideally restrict it to just the things that will be the flip-flop. If I add extra stuff like next state logic and things of that sort, it'll blur what's going on inside here. So it'll make it harder for it to infer because I tell it this is a flip-flop and I add a bunch of other stuff to it. All right? Now it's got to figure out where's the line between the combinational circuit to prep it, kind of get all the next states together, and the part that's actually going to just be the memory. So make it really easy. Remember, computers are actually not very smart. They're great at running out code, but they're not smart. So make it really easy to figure what you want built, and then it will build the right thing for you. Okay, so this one is going to be specifically just, you're telling it, build me a flip-flop. Right, and so a flip-flop means that we want it to be controlled by an edge. What's a latch? Maybe I should specifically say memory controlled by edge for this, for a flip-flop. What's a latch? double slashes. That's a comment. A latch is, it's memory again, right? But what's it controlled by? Well, it's not an edge anymore. It's controlled by either high or low, right? A high-low signal, you can think of that as an enable. So if it's got an enable but not a clock, essentially, then it's a latch. Right? So the high-low state of that enable signal, it might even be a clock that's going in, but the clock is being used as an enable. Whichever way you're enabling it, high or low, that's the only time it can change. Why make the big difference between these two? Each of them are controlled by a single wire signal. So who cares? Imagine for a sec, we're trying to find glitches, right? So imagine, glitches are crimes to us. If I could tell, the police force, there's going to be a crime at exactly this time at this location, do you think that's more helpful for saying there's going to be a crime at this location somewhere in the next week? Which one's more helpful? Yeah, if I could tell you exactly when it was, that would be a lot more easy, right? You could go down and you could check that one spot, right? Well, in your design, you're the policeman. You're looking for the glitch, the error, to remove it. If you know exactly when it is, it's much easier to remove than if you know somewhere in this zone. Latches, it's somewhere in this zone. Flip-flops, it's exactly here. That's really the difference. Right? It's just when it can change, which gives us that opportunity. We limit them. So, I really want you to ideally use this one and this one. You should almost never use this. And you should only use this if you really know you want this. Why would I ever want this then? Why even build something for it if it's so dangerous? This is memory, and it's really stupidly fast. Okay? So this is kind of as a super fast thing to change. It's a less complicated circuit, so it's smaller. It's all kinds of other stuff. So this is like your super fast race car, and this is your very useful, minivan or something, right? I wouldn't necessarily want to take an Indy race car to the grocery store. So as a general rule, this one is safer. But if you want speed, this is your one, right? So now you know the requirements on them, so you decide, but this is now dangerous, you'll have to put protections. It make sense? Okay. So we're telling it here that I want a flip-flop. You don't have to put the flip-flop. If you don't, you're telling it to figure it out on its own. I still have to tell it when to edge trigger. So I can say, for instance, at pause edge of the clock. Right? And I don't have anything else here to worry about, so I can just put this. Alternately, I could be doing neg edge. You got to determine which one's useful to you. All right. So I've got that first part. This is where I want the memory transfer to go. So there's only this behavior. And since if I'm inside here, this has been satisfied. That's what this at side, this is the event. So if this code is running in here, it's telling me what's happening at that edge. There's no reset or anything, so I only do one behavior. And what is that behavior? For a D flip-flop. What does it do at the edge? Okay, so it can do the off or on switch, which means this is where data gets loaded. Right? So all I have to do here is to do the behavior of this, right? Q gets the value of D. All right, my Q is a reg, so I can just say Q, that's the value of D. I think I capitalized them, I did. All right. So this tells me the exact behavior of this. Why do I do this less than equal here? Yep. Whenever you're in these flip-flops, if you're in a flip-flop, do this. When you're in combinational logic, do the other one. Okay. Now, technically speaking, you can do either one at either spot. The importance of this distinction gets to when within a simulation the event happens. This is actually the whole difference is really, it can infer the right thing at this point, but to make the circuit work right, we have to do the timing of when we update signals that are constantly updating. We want to do that at a different time from things that update at an edge. They've got to happen at different time periods. So in your simulation, we have to do them at different sequences inside the time. So it can look at these things and tell when to do it on its timing inside. Even inside when it's the same time period, they will actually update slightly differently at their time to maintain the functional behavior of something that looks continuous versus something that looks discrete. Okay? That's why this is really there for the simulation. And if you don't do this, your simulation will not look like your real code, and you won't know why. So you're doing this really to make your simulation match the physical hardware. That's the whole reason for doing this in a flip-flop. Okay? It's just to aid the simulator. Does that make sense? Okay. So at that point, I've done my always. That's everything that is described here, so I can just end my module. Now, let me ask you for this setup, right? This is a fairly simple setup. What would I do to check this? What would you want to see inside of a some type of a test bench to walk through this code? So when you're thinking about this, think where could it go wrong? First, try to figure out from your perspective of the design, where could the design go wrong? What might the machine infer that, how would I tell that it inferred the wrong design? What if it, if I hadn't included this underscore flip-flop, what if it built me a latch instead of a flip-flop? Well, I need to be able to check that, right? So I want to make sure anything that could happen differently than what I'm expecting, I need to check to find out, did it do what I was expecting it to do? Okay? So that's what you want to start. This is the first level of it. Right? You want to figure out where might it have inferred the wrong design and find a test to see if it got the wrong design. Right? So did it infer the wrong design? Or the wrong component? All right. These are things I'm thinking for on my test. What other things might I want to check in just any old test bench? What's that? Okay, so I might want to check something just on kind of the clocking behavior, and does it respond? Is there, beyond what, it could infer the right thing, but it could still have something that doesn't react fast enough, right? The latency could be wrong. What if it doesn't have the right setup and hold? So I want to check to see that these parameters on my component, if it inferred the right thing, is it good enough, right? So I'm going to want to check things like my clock and other stuff, right? Did the device work? It inferred the right thing, but does it really work? And so, some of these could be things like design errors. There could be things like it's not good enough for the spec. So I could look at, what are the customer requirements and things of that sort and make sure that it meets them, because not everything's going to be fast enough for them. We've talked some things about some of the timing and that it has to get the times of flights and that. We can measure all those and see, does it meet them? Right? So I could check all kinds of stuff related to that, and I would want to say, okay, what characterizes that? Right? Where I could find, where it doesn't meet the specs, and create something that happens that meets them. This is why we do 10 nanoseconds for a clock cycle. If I need something that's a little better than that, right? What if the crystal's a little bit slower or whatever? I offset that clock a little, make it a little bit slower, and then I come in and I put a test case where it's operating on the original requirements, and I see, does it mess up the system, right? Or was it robust for those time periods and it still kind of functions even if the signal has transitioned slightly different? Does that make sense? So I would translate all these things. I'd find out what characterizes a problem, right? So the speed will be how much delays, those hashtag numbers you put in there. Those delays are what will let you meet the time requirements in those specs. And if the problem happens by, particular input and output combos, right, we would just change the values that are transitioning. And that's our two dominant areas inside. All right. So these would be all things I would want to check. Is there anything else I might want to do? Can all of you predict all of these? Do you think you can figure out every error? Do you think anybody can figure out all the errors? Right? Yeah. Right. We're humans. We're finite. We're going to make mistakes. So I might want to make something that's kind of like a catch-all, right? I kind of put in what I expect are going to be the problems and check as many of them as you can think of. But I should add a few things that will check stuff you didn't think of. How can I check something I didn't think of? Randomize. Right? I can randomize some of my times and things like that. I can take my customer specs. I can put what are called the constraints. I can use these as constraints and have it pick random numbers within those constraints. Right? So we'll also have a third one, which will be, random within constraints. And these constraints are designed to meet customer specs or design requirements or whatever you want to consider those. Fair enough? So I would come in and write a test bench based on all these cases. I'd walk through, I'd generate cases for them, I would test them. And to make sure, did it get the right design? Does that design work if they do get the right design? And then a couple random ones just to make sure things I didn't expect were checked anyway. Right? Those are the big categories. Right? Now we haven't told you, there are ways to do randoms within your simulation sets. The basic Vivado doesn't do the greatest job with these. So to really do a good job of these, we have to go to a fancier simulator. So that's why we leave that to the second course, because I don't want to teach you a whole new simulator halfway through. And Vivado is used very heavily in industry because it's cheap, it's readily available, stuff like that. But it's not always the best one. Could I still do random even though it doesn't? It does some random stuff, but not always all of them. Could I do really good random inside Vivado? You can, it just needs a little help. How might you be able to do this inside Vivado? What if I generated all these random things inside of a C code or a Python code, and I outputted all the things to test? So I did the randoms in advance. And I could put all the constraints like C or Python is going to be more than capable of handling all those constraints, because they're very generic programming languages. So I can use all of their randomization skills and constraints and things, generate my numbers and the results, write my expected results table, all that, dump them to a file and just read those in. So even though, Vivado doesn't have the ability to do all those randoms in, I can force it by an external program doing it in advance. Okay, do we feel a little better about what I can do with tests? So I put this in because anytime you build something, you ought to think about these. And it's almost always these same basic ones I care about right now. All right. We feel good with this? So let's step up, right? We're going to move up, and I want to add several things now. Because the next thing we're going to care about on our design is to add things like, for instance, I want a reset. And I might want an enable. Now I'm adding both of these because the addition this does is kind of twofold, right? And what I mean by it's kind of twofold is I've added different signals that are competing alternate ways, right, for the clock. Because the clock says, if it's a clock pulse, I want to let Q get D. The enable kind of scopes this one's control a little bit, right? I only want to do that if enable allows it, so it's kind of like a gatekeeper. And reset is kind of like the, if I press reset, you must listen to reset, go to 0. Does that make sense? All right, so all of these are controls that override, and they have various levels of importance on the signal. Who has the biggest control? So since the real big difference is who has control, we've got to code them in such a way it can recognize that control sequence is right to see which one has priority. And we also ideally want it to recognize this device so that if it just has that built into it, it'll just use this instead of actually generating something. This is the really important part, for instance, for when dealing with an FPGA, because your FPGA does have a system that has D flip-flops with clock, enable, and reset built in. So ideally, I wanted to infer that device rather than building one, because something that's been hard built will always be faster and less problematic than something that's inferred on the fly. Does that make sense? Okay, so let's write our code. All right, module D flip flop, right, with reset and enable. So I'm just kind of adding them on so I can remember what everything that's involved in it, I stick it within the name. All right, my inputs, in this case, will be my clock, my reset, my enable. I have an input, that's my D, and I'll have an output, which will be a register, which is Q. We agree? Now I've separated these on different lines because these are all control signals, and this is a data signal. I didn't make that distinction before because it was way too small, so who really cares? It's easy to see. When I start getting a bunch of signals, it is nice to kind of group them into those areas because control and data kind of mean something different to us, particularly when you get to later designs on computer builds. All right, functionally, they are different. Like, for instance, on clock, we have a different layer on FPGAs, right? The clock signals are separate from your data signals. Okay, so far so good? Okay, when I get into building this, so I've got my same always. I guess I start with the blue for my optional, right? So flip-flop is optional. Again, it could be very helpful here. The first thing is I want to know what happens after this event specifier, right? What do I include? We've said clock goes in here. Yeah, bless you. All right, what else? So why does reset come in here? Could I just close this and reset would still work? Yeah, I can make reset still work even if I don't include it here. What would be the difference in the design it would build? Functionally, what's different if I don't include it? If it's not in here, then it can't update, right? This tells me that the positive edge of a clock is a time when it can update. So that means if I don't include anything else, all of my other signals are called synchronous signals. They can only update with the clock. That makes the clock dominant, right? Because the reset signal, even if you push it, has to wait for the clock to let it happen. So if you want something to control when something can update, well, clearly clock has to be able to, otherwise you can't build a basic flip-flop, right? The data part won't work. But if I don't include reset here, then reset becomes subordinate to the clock. It's a synchronous reset. But what happens if, like, the very problem I'm trying to fix is the clock gets messed up? It is possible that inside my system the clock might get up, and if I reset the whole thing, it might start the clock again. Okay? So that might be something I'm trying to kickstart here. Includes the clock. So the clock has to be subordinate to reset because reset needs to fix everything in case there's a problem. And I'm not sure clock's always going to work. So that's why I want to make reset dominant, is I have to give the user dominance. So the whole importance of reset being asynchronous is to give the user control. Right? Any of you ever have your computer freeze on you? What if they don't include a button to let you do that? When it freezes, you just got to wait for the computer to come back working for you. How happy are you? Right? Now you're trying to pull the power cord. Well, what if I'm like, I'll protect them. I'll put a battery backup in here. You pull the power cord, it still keeps going. Are you happy with me? But I made it safe. Right? If you don't give users control, the human has to always override. Okay? So that's why the reset must be dominant. Does that make sense? So understand your whys when we're going in here. Reset is for human override. So we're going to want also our pos edge of reset. I'm not putting enable in here. Why not enable? Yeah. I want to precision time it. Reset is my override, so it can happen whenever it wants. But everything else must be timed according to the clock because the timing of the clock allows me to rule out the glitches. I can't rule out the glitches if it also depends upon the timing of enable, because who knows when that gets here. Right? I only want to time to one thing. It just makes it easier for my system to check. Okay, so for system checking and validity, that's an important one to do. So those are the only two that go in here. And that's the reasons why, what you want to think about. So that's how you want to infer them. Okay, next part. All right, I've got this. Now what's the order that I want to check these in? Who goes first? I mean, right now we typically have done things like this, right? If reset equals 1. But couldn't I have done if reset equals 0? Programming-wise, does it make a bit of difference? Or simulation-wise, does it make any difference? No. Does it make a difference when it infers the build? It does. This is why reset equals 1 in this case, right, from this pos edge of reset, has to be first. Because who's most important of my three signals that's being sent out? Reset. Why is reset the ruler here? Because the person is in charge, not the machine, right? So reset, the person always has to be able to recognize it's a problem, you're doing something wrong, reset, right? So you have to give the highest control to the person. The highest control must happen first because there is going to be a priority that is assumed from the sequence. When it goes to build or infer a design, it will infer priority by order. So if you put checking the clock first, it's going to think you want the clock to be dominant. If you put enable first, it's going to assume enable is dominant. If you put reset first, reset is dominant. Do I have to do this double equal one? Why? Yeah, if I put a single equal, it would definitely be assigning me a value. What if I didn't do anything here? What if I just said if reset? Yeah, but isn't that what I'm checking? So this technically, I really should have written this in blue. Because since it's a single bit, I can treat it just like a logic function. This gives me a single bit output, true or false. But reset is a single bit, true or false. So since you're checking is reset equal 1, it's equal to the check. So I could just put if reset. Which do you think would be easier for it to figure out your design intent? This, or just saying if reset? Well, if I told you reset double equals 1, what's the first thing you're going to do? Yeah, you're going to check in, you're going to do this check. This would kind of suggest that you do an extra process. So that would naturally tend to infer a slight design build. I'd have to build this check-in, as opposed to just checking the value of the bit. If you treat this as a Boolean, you're checking it as the result. So this actually would imply a simpler design if I didn't include the double equal. So it's slightly, in both cases, a decent compiler will infer it. This one would be slightly easier without the double equal to infer the design you want, to just use that one as the selector. Yeah.
So would using the double equal sign be safer?
Actually, not using the double equal is slightly safer. It's not a huge difference, right? But it is actually slightly safer because if I just put that in, I'm telling you the data bit itself is the check. If I put this, you could infer, right? This double equal can be taken as there is a circuit called an equality checker, right? And it takes two numbers and it gives out a result. Is it equal or not? So it takes in two different numbers of however many bits, and it gives a single flag, true or false. All right, so this is an equivalence checker, and we'll get around to looking at some of these, but that's actually technically what this says. Now, since so many people do this, we try to code our stuff to look at this and say, oh, I can just do reset, right, as the result and simplify it. If you just put reset in, you've removed one step of requirement for it to make that inference. So that's why I say it's a little safer. Most people put those in, but not everybody does. So that's why it's slightly safer. Does that make sense? All right. Everything you write implies a circuit. And if we know what you want, we will sometimes make an alternate choice. So the question is, did you want me to build this or just use that value? Well, ideally in this case, we just want you to use that value and just realize that is a reset bit that's asynchronous. And so you can tell this is a reset bit from this function here, and it's the highest priority and it's asynchronous. So that's what it's telling me when you do that. Right? So at this point, this is where I say that my queue gets the value of whatever you want it to be, 0 or whatever. I'm not specifying the number of bits here. All right, this technically works no matter what, it'll truncate. All right. For the enable, what do I want to do? Do I do enable or clock now? Yes, that is correct for here. Why? Isn't clock more important because I only do things on the clock's edge? Yeah. So if you have already gotten to an edge, and that's what this asserts, so you're guaranteed to be at an edge, and I'm not at a reset, which is my highest priority, then which is more important, assuming I'm at an edge, clock or enable? Well, clock doesn't have any control. It's just gates are wide open. Edge was met. I don't care anymore, right? But enable does have a control to say. So you have to check its control. So that's kind of the next one that's going to come in. You want to put your else if to check to see if that enable is true. All right, so I can say enable here, and I've got the option of equals 1. Can I ever have enable low? Yeah. Yeah, it's a premise. And so that will come out on when people build them and they fabricate. Remember at the very beginning, we kind of built the transistor things to make the gates? And remember, it was sometimes easier to have negative inputs or outputs on them just because that was less number of transistors. So it could accomplish the same value, but it was either high or low on the input or output. Like, it was easier to do NORs or NANDs. Those were smaller than ANDs or ORs. Okay? So we said, hey, if it's smaller has all these advantages, right? Less power, less heat, all this good stuff. That's going to be true when we build it here. So sometimes it's easier to have the enable low just because it's easier to build. Okay? So we often want to adapt that. Sometimes you'll also do it because like on buses, it might involve less power, believe it or not. You actually only pay the power when you do a transition. Right? There's a small amount of power when it's running, but it's pretty small if you did your design well. So most of the time you're going to just pay for the transitions. So it doesn't really matter high or low for most of your power, so then it's, whichever one involves easier for flips. And sometimes that's easier the other way. If I want to do it low, would it be required to do the double equals 0? It certainly is an option, but it's not the only requirement. What else could I do? I could knot it, right? So I've got tilde or bang or double equals 0 as alternatives. Of those, which one do you think would be the best? Right, I've got my options for 0, so this is an aside, right? Aside if enable was 0 was my one. Do I want the double equal? Do I want the tilde? Do I want the bang? Which one's best? The way you can tell is what is it going to infer as a circuit. If I do double equals 0, what's the circuit going to look like? Well, it could infer this, checking against 0, right? What happens with the tilde? A tilde just means bit flip, so it's a true NOT gate, right? Or a low voltage, it just flips the voltage, right? What does bang do? We say it's no different if it's a single bit, but if it goes to multi-bits, it's actually saying, do another condition check for me and see if it's equal to all zeros and output a Boolean. So this one builds a fairly big circuit. This one builds a very similar looking circuit. This one just inverts the voltage. Which one is simplest? That one is. Just flip the voltage. So this is my favorite. Right? Because it gives me the simplest circuit. That's why I'm saying when you're thinking about these, right, the actual code is stupidly easy, right? But every little location means something. So that's why I want you to think about it here. Right? That is the simplest. So if I had the equal zero variety, it would be better to just do tilde enable. It would also be easier for it to invert it at, or understand it as an enable low. All right. What happens if my enable gives me a yes, go ahead? If it says go ahead, then Q gets my D. Do I need the else? If I don't put the else in, what happens? So there is a potential of a problem here. But if there's also something where somebody could say, hey, you know what to do. I'm only telling you to do something. If you don't do this, you shouldn't do anything, which means leave it alone, which is hold. So there's an inferable thing of just leave it alone, which is what we want. All right? So the question is, what is it going to understand to do? Does that make sense? Now, if doing this, if I don't include the else, which is optional, else, right, and I don't really particularly like this syntax, right, but that's really what you're saying needs to happen, right? It gets fed back around. But I want to have you understand something that happens here. This syntax right here implies I've taken the wire and I've plugged it back into itself. Right? Remember, anytime you have a single wire name and you plug it in, it's literally saying it's a contiguous wire. There's no device between them. Does that make sense? That's what can be inferred from this, from the circuit diagram. If you want something other than this, you should have a separate wire and do some, how do you get the one from the other and then feed it back in? That would make them separate with a device between them. This one literally means hook the wire back around. If I hook that wire back around, that technically is a latch. So if you didn't have the always underscore flip-flop, and you didn't include this, it will infer a latch, which is your error. That's the error it will get. It will infer a latch, and it'll give you a warning and saying, such and such is a latch. It won't be an error, though, because you could have meant that. Right? So if you ever see this, where it's on both sides, it's gonna infer a latch. It's almost always not what you want to do. But that's technically what you told it to do. If you use these, it knows not to do that, right? This allows us to pick flip-flop and comb separate from latch. So we can tell it, no, don't ever infer that. Since I told it not to infer it, leaving it off, which would have inferred that, won't infer it because you told it don't infer it. So it will just correctly hold it and away you go. So if you put that underscore flip-flop, the error is removed. So you really, for safety's sake, should warn it, right? And the easiest way is to do this and just leave this off. Does that make sense? That makes it easier for it to make the inference because it doesn't have to do any inference at all. It knows it's a flip-flop, and then all it has to walk through is say, right, it says, I know it's this, and then it has to just connect my signals to which ones go where. Well, it's coming in on this side, so I go, oh, that's my data, right? on the output